Section 20.6, series wiring. Up to this point, we've looked at simple circuits where we have a voltage source like a battery and a resistor, like our flashlight. But there are many circuits in which there's more than one device that's connected to the voltage source. So there's a couple of different basic ways to wire these. Sometimes you can combine them, but we're going to focus on the two separate ways first. One of those ways of wiring is known as series wiring. Series wiring means the devices are connected in such a way that there is the same electric current through each device. So that's the key. If they are in series, then there must be the same current through each device. Series you can also think of is when you're going to hit, if you follow the current path, it will hit one device and then it will hit the other device. It'll encounter each electrical resistor in series, one after another. So here's a schematic of one example of a series wiring, right? We have our voltage source like a battery down here with a positive and negative side. That generates a current that flows out of the positive terminal and encounters one resistor and then the other resistor. Now each of these resistors is going to then take some of the voltage away, right? This is removing some of the potential from the circuit. So the one will take some of it away, the other will take the rest of the voltage away until we go back down to zero, and the battery then restarts the process. Kicks the charges up to the high potential so that they can flow through the circuit. So let's take a look at how we can describe these resistors together. And to do that, we're going to relate this voltage of the battery to the voltage across the first resistor and the second resistor. And it turns out the voltage across the battery is going to be, the voltage gain is going to be equal to the voltage drop across resistor 1 and resistor 2. Resistors 1 and 2 use up all the voltage that is present. So we can note that in this way, that the voltage of the battery is equal to V1 plus V2. Now using Ohm's law, we can say that V1 is equal to the current times resistance 1, and V2 is the current times resistance 2. Now notice the current doesn't have a subscript here. Why is that? Well, because we're in series, the current is going to be the same through each of these. Both of these will have the same current passing through because we can't have the current suddenly like surge in value. This is a steady circuit. So the current will stay the same. That means we can factor it out of this expression and write it as current times R1 plus R2. And we could then describe this R1 plus R2 as just R sub S, the resistance of the series resistors. So if you have resistors wired in series, this is a way to create an equivalent circuit and say that the net resistance, R sub S, of your resistors in series is just adding together resistance 1 plus resistance 2 plus resistance 3 plus however many you have. And that allows you then to draw your circuit. Instead of having 2 devices or 3 or however many you have, you can draw it as just a single resistor, which we could label R sub S, that is then connected to the battery. So we found a way to make our circuit much simpler, where we just have a single resistor in effect. And we could always go back to having multiple resistors, but it can be nice to have this simpler view of it. Let's try this out with an example. All right, so example 8, resistors in a series circuit. A 6 ohm resistor and a 3 ohm resistor are connected in series with a 12-volt battery. Assuming the battery contributes no resistance to the circuit, find A, the current, B, the power dissipated in each resistor, and C, the total power delivered to the resistors by the battery. So notice we have 2 resistors and the battery, and it tells us they're connected in series. Based on the information given, you should be able to move to drawing a picture like this. That we have the 12-volt battery, and that is wired up to the 6 ohm resistor and the 3 ohm resistor. and they're wired one after another because they're wired in series. Now in A, we want to find the current. If we want to find the current, it's a little tricky because there's two different resistors there. But if we can find the equivalent circuit, it becomes easier to find the current. So to get the equivalent resistance, we need our RS equation, where remember RS is just adding 6 ohms plus 3 ohms. And that will give us 9 ohms for the net resistance of the circuit. We already know the voltage here, so if we know the resistance and the voltage, we can calculate the current using Ohm's law. So we know that the current will be equal to the voltage divided by the resistance. If we want to find the power dissipated in each resistor, how do we go about doing that? Well, we have a number of equations for power. We have P equals IV. We also have P is equal to I squared times R, or P is equal to V squared divided by R. So what's the best one to use here? Well, one thing that's worth noting with this problem is that these two resistors each have a different voltage across them. And we don't know what that voltage is. We could calculate it using Ohm's law, using each of the individual resistances with the net current passing through them, and we could calculate those voltages, but it is one extra step. So what's more direct is if we want to find the power using something that does not have voltage. So if we can use this I squared times R, that will help us to solve for the power more directly. All right, so let's give it a go. So again, the series resistance, we can just add those resistors together. 6 plus 3 equals 9 ohms. Awesome. And then finding the current using Ohm's law, V divided by the series resistance. So 12 volts divided by 9 ohms comes out to 1.33 amps. If we want to find the power dissipated by each resistor, then we can note that we can use this I squared times R equation. So the current is the same in both cases, and then we're just multiplying by that resistance. So it comes out to 10.6 watts for 6 ohm resistor, 5.31 watts for the 3 ohm resistor. Now, what's the total power supplied by the battery? That's just going to be however much power these two devices use up, right? So we can add up those two to find that the power supplied by the battery is 15.9 watts. So this highlights series resistors and how we can calculate the power through them, which is a useful calculation. One application of series resistors is with personal electronic assistants. So anytime you are writing with a stylus that's not electronic, so a common example of this is at the supermarket when you go to sign your name, right, on the little credit card thing. The stylus isn't electric, but somehow the pad knows exactly where you've placed the stylus. How does it do that? Well, there's two transparent conductive layers, and when you push the stylus down, it brings them in contact so that a current flows between them. And the current will flow through two different resistances, one on the top layer, one on the bottom layer, and it can use those resistance values to pinpoint exactly where the stylus is, and then mark that pixel and leave a mark there just where you placed the stylus. So this is using the idea of series wiring in order to create a very simple way to write on an electronic device. Pretty cool. We will see the other primary way that we will wire circuits in the next video, so you're going to want to see it.